SPH4U Modern Physics 6.2 Quantum Theory. Planck's quantum hypothesis. So in the study of black body radiation, there are discrepancies between theory and experimentation. So black body is an object that completely absorbs any radiation falling upon it, and black body radiation is the radiation that would be emitted by an ideal black body. So since this black body completely absorbs any radiation falling upon it, then all this radiation, anything that you can observe from it, is radiation being emitted off of it. So Max Planck, he formulated a hypothesis to account for these discrepancies. So he stated that the energy radiates from vibrating molecules in bundles, which are called quanta, and it's given by this equation. So the energy of a quanta is equal to h times f. F is the frequency of the light that is of the light, and h is Planck's constant, which is equal to 6.63 times 10 to negative 34 joules times second. So this is an important equation. So one important point to know about Planck's quantum hypothesis is that this challenged the classical belief that light traveled like a wave, because EM radiation does not transmit energy in small discrete packages such as quanta. So this started the concept of the particle theory of light. So we had to calculate the energy in both joules and electron volts of a quanta of blue light with a frequency of 6.67 times 10 to the 14 hertz, and a quanta of red light with a wavelength of 635 nanometers. So we know that the frequency is equal to 6.67 times 10 to the 14. And so we have E is equal to HF. So E is equal to 6.63 times 10 to the negative 34 times 6.67 times 10 to the 14. So E comes out to be 4.42 times 10 to the negative 19 joules. Now to find this in electron volts, we would just do 4.42 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19. This comes out to be 2.67 electron volts. So now we had to do it for a quantum of red light with a wavelength of 634 nanometers. So they called the wave equation that we had V is equal to F lambda. So V over lambda is equal to F. So V, since this is light, this is C. So C over lambda is equal to F. So wavelength, if we translate it into meters, 6.35 times 10 to the negative 7 meters. So E is equal to H times C over lambda. So that's equal to 6.63 times 10 to the negative 34 times 3 times 10 to the 8 over 6.35 times 10 to the negative 7. So this comes out to be 3.13 times 10 to the negative 19 joules. So 3.13 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19, that's equal to 1.96 electron volts. So now we're on to the photoelectric effect. So Heinrich Hertz realized that certain metals lose their negative charge when exposed to ultraviolet light. So this is called the photoelectric effect, where UV light releases electrons from a metallic surface. So photoelectrons are emitted from the photoelectric surface when they're hit by FO, or the threshold frequency. The threshold frequency is a certain frequency that is needed to release electrons from the surface of a metal. So the threshold frequency varies depending on the metal. So the intensity of the light has no effect on the threshold frequency. So if F is below FO, so the frequency is below the threshold frequency, then not a single photoelectron will be emitted. So if the intensity is above FO, then the current of photoelectrons is directly proportional to the intensity of light, and the max kinetic energy is directly proportional to its frequency. So now we're going to look at Einstein's analysis of the photoelectric effect. So when light strikes a photoelectric surface, it absorbs energy in discrete amounts called photons. Thus, the work must be done to free the electrons from the surface. So E photon is equal to Ek max plus work. So Ek max is equal to E photon minus work. So if you remember what the equation for the energy of quanta is the same for energy of photon. So E photon is equal to HF. So Ek max is equal to HF minus W. So we can actually plot this. So if we have on the y-axis Ek max, and on the x-axis the frequency, and we have this certain FO, so the x-intercept, that's the FO, so this is a certain frequency. The distance between the x-axis and the y-intercept, that's the work required for this frequency. So if we have another frequency here, this is FO1, FO2. So this meets the y-axis here. This is the work required for this one. And something interesting about these frequencies is that their slope is the same. Their slope and shape is the same, and the slope is actually Planck's constant, which is really interesting. So this is an example of a question that deals with the photoelectric effect. So an orange light with a wavelength of 6 times 10 to 2 nanometers is directed at a metallic surface with a work function of 1.6 electron volts. So work function, that is the W that we saw in the equation on the last slide. So we have 3 things we need to do. We need to find what the max kinetic energy is, what's the maximum speed, and the current potential necessary to stop these electrons. So what is the max kinetic energy? First, we should convert everything to meters and to joules. So this the wavelength is 6 times 10 to negative 7 meters, and the work function, let's convert it to joules. So work is equal to 1.6 times 1.6 times 10 to negative 19, so 2.56 times 10 to negative 19 joules. So what's the max kinetic energy? Ek max is equal to HF minus W, and we know that F is equal to C over lambda, so H times C over lambda is equal minus W. That's equal to max kinetic energy. So now we get to sub everything in. So 6.63 times 10 to negative 34 times 3 times 10 to the 8 over 6 times 10 to the 7, negative 7. This is minus 2.56 times 10 to negative 19. So Ek max comes out to be 7.55 times 10 to the negative 20. So this is max kinetic energy. So now we have to find the maximum speed. So let's do Ek max is equal to 1/2 mv squared. So we rearrange v is equal to 2 times Ek over m. So velocity is equal to 2 times 7.55 times 10 to the negative 20. This is over 9.11 times 10 to the negative 31. That's the mass of an electron. So velocity comes out to be 4.07 times 10 to the power 5 meters per second. So the cutoff potential necessary to stop these electrons, so let's make EK equal to EE, electric energy. So EK is equal to QV, so charge times voltage. So voltage, so the cutoff potential, that's the voltage. So voltage is equal to EK over Q. So that's equal to 7.55 times 10 to negative 20 over, so this is over 1.6 times 10 to negative 19. So this 1.6 times 10 to negative 19, that's the charge of the electron. So this comes out to be 0.472 volts. So there we go. So now we're going to look at the momentum of a photon and the Compton effect. So Arthur Compton directed a beam of X-rays at a thin metal foil. So he observed ejected electrons, but also an emission of X-ray photons lower in energy and frequency. So the Compton effect is that electrons were scattered and angled to the X-ray photons. So the X-ray photons collide elastically with an electron. So the electron flies off with this new energy that is grabbed in the collision, while the X-ray photon decreases in energy since that energy was transferred to the electron. So we can find an equation to represent the momentum of a photon. So we know E is equal to mc squared, and that P is equal to mv, so momentum is equal to mass times velocity. So if we rearrange E is equal to mc squared, then we get m is equal to E over c squared. So P is equal to E over c squared times v, but this v is actually also another c, so this gets simplified to P is equal to E over c. P can also be represented by equation h over lambda. So these are the equations for the magnitude of photon momentum. Here's an example of a question that deals with the momentum of a photon. So a photon of wavelength 500 nanometers has the same momentum as an electron traveling with a certain velocity. Find this velocity. So first we should find the momentum of the photon. So I have this equation. P is equal to h over lambda. So that's equal to 6.63 times 10 to the negative 34. This is over 500, so 5 times 10 to the negative 7. So that comes out to be 1.33 times 10 to the negative 27 kilograms times meters per second. So now we have this equation, and we have this. P is equal to m times v. So v is equal to P over m. So this is to find the electron. So velocity is equal to 1.33 times 10 to the negative 27 divided by 9.11 times 10 to the negative 31, which is the mass of electron in kilograms. So this comes out to be 1.5 times 10 to the power 3 meters per second. So light acts as both a wave and a particle, but not at the same time. Instead, it depends on the situation. So this is light's wave-particle duality. So I'll just show you a derivation here. So we know the momentum is equal to h over lambda. So lambda is equal to h over p. We know that P is equal to m times v, so we know that lambda is equal to h over mv. So this is called the de Broglie wavelength, and it shows that particles actually exhibit wave-like properties, which was an extraordinarily radical thought at the time. So EM waves, they act as a guide to where a particle should be moving, and it predicts the probable behavior of that photon, which is a particle. So that's the wave-particle duality of light. Here's a question that deals with the de Broglie wavelength. So what is the de Broglie wavelength of a 100-gram ball moving at 19 meters per second? So 100 grams, that's 0.1 kilograms. So we know that lambda is equal to h over m times v. So that's equal to 6.63 times 10 to negative 34 over 0.1 times 19. So this comes out to be 3.5 times 10 to negative 34 meters. So that's the de Broglie wavelength of that 100-gram ball. So this was the last lesson of this unit of SPH4U, Modern Physics, and this is the last lesson of content for SPH4U. Thank you.